The Best of Our Knowledge explores topics on learning, education, and research. Coming up, scientists have discovered a new color. Only a handful of people on Earth have seen Olo, a greenish-blue hue that can only be seen by using special equipment. And we'll learn how researchers are aging stars, not by the light they emit, but by their sound. I'm Lucas Willard, host of The Best of Our Knowledge. This is The Best of Our Knowledge. I'm Lucas Willard. Only a handful of people have seen Olo. That's because the color described as a saturated, vivid blue-green cannot be seen by the naked eye. A team of researchers at the University of California, Berkeley, led by Dr. James Fong, used technology called Oz to use lasers to control photoreceptors in the eye, revealing the new color. Hannah Doyle, a research student at Berkeley, is one of the few people to have seen the color and joins us now.
It's all kind of based on this technology called adaptive optics scanning light ophthalmoscopy. This is like an optical instrument that allows you to image the retina, the back of the eye. And there's kind of been a lot of work over the years developing this technology and trying to get really high precision stimulation of the retina with it. And James especially, and a lot of the other people who worked on the project improved its functionality in order to be able to simultaneously image the retina, track the eye's motion, and then deliver laser stimulation to individual cone cells in the retina, like thousands of cone cells at a time, which before had not really been possible. So that's like the idea behind the technology. And then we had to design experiments on top of that to kind of probe what colors people were perceiving with this technology and quantify them in some way.
So what led you to be able to then see and discover this color Olo? O-L-O, it's spelled.
Yeah, so part of one of like the guiding questions that spurred the Oz project to even begin was, what do we see if we only stimulate the M cones? So under normal viewing conditions, there's no light that can stimulate only the M cones in isolation. So I'll take a step back. There are 3 types of cone cells in the retina that are each sensitive to different parts of the visible spectrum of light. They're referred to as L, M, and S cones because they're sensitive to relatively long, medium, and short wavelengths of light. But the M cone sensitivity overlaps completely with the L and S cone sensitivities. So normally they are never activated on their own, but through the Oz vision system, we can spatially restrict light to only target the M cones. And the question is, what does someone perceive when you do that? Because that's a viewing situation that doesn't happen normally.
Right. So normally when you're using your eyes to look at something, the cells in the back of your eye can detect different kinds of light, which then your brain sees as color. But there's a few different kinds of cell in the back of your eye. And one, the M, might be a little more powerful, to use that word, than the other kinds of cells. Is that correct?
Yeah, the M cone cell is kind of in a special situation because of the overlap in sensitivity that it has with the other 2 cone types.
And so when your face is up to this machine and it's switched on, and there's this very specialized kind of laser light that is sent to your retina, what is actually visible? When we talk about being able to see Olo, what does it look like?
Yeah, so I am one of the few people who's been able to see it. I didn't get to see it for like the first round of subjects that we had, but I have seen it since. And I mean, the experience is you uh, sit into the system. We have to keep our head really still. So you have to bite down on what's called a bite bar, which is kind of like you make a dental impression, and then you bite down onto that. And then you just see like a square kind of like floating in space. Um, because of like some technical considerations, you actually have to fixate your gaze a little bit away from that square so that the laser light can land on the correct region of your retina. So you're looking away from the square, and then you see a colored square a little bit displaced from where you're looking. And then as for Olo itself, I would describe it as like a very rich blue-green. We do all the visible stimulation with a just regular 543 nanometer green laser. So normally, if you were just looking at that laser, it just looks kind of like emerald green. But then when you turn on this very like specialized stimulation, it's very obvious that the color like changes completely, which is very cool to see.
What was that moment like? And when you saw this Olo square, did it seem unfamiliar to you? Did it seem, I've never seen that color before?
Yeah, so I would say for me, like it wasn't a surprise at that point because I we had already been running experiments for a long time, and so I kind of knew
So you're a little
what to
jaded
expect.
about it, I guess. No.
I would say that like because the hue of it is describable, like you aren't it's not an unfamiliar hue, like it's blue green. Um the saturation of it is like really what's novel, and one of the ways we're able to like really measure that is we had subjects look at the Olo stimulus and then try to match it with the nearest uh, just like regular monochromatic laser source. And at least the reports that I've gotten from subjects is that the nearest monochromatic light looks almost pale in comparison to the Olo because the saturation level is so different.
There are now products being sold on the internet that I've seen with, Olo paint or Olo this or Olo that. Does any of this stuff that's now floating around on the web, does it even compare to what you saw in the Oz machine?
Um, yeah, you really can't, reproduce it by nature on like a conventional display or with a paint. So we tried our best to give people a sense of what the hue looks like. That's something you can communicate visually. Um, so it's been really fun to see like all of these kind of offshoots and products and comments that people have given about it.
Now, this also brings to mind the special glasses that look almost like sunglasses that individuals who experience color blindness can wear. And it allows, through filtering the light, people to perceive colors that they normally wouldn't be able to. Is this fundamentally a similar kind of technology?
I would say it's uh what those two things do similarly is that like in the Oz system and in those glasses you can create higher contrast between the signals that the different cone types are receiving than like normally would happen. Um, in Oz, because we can completely like spatially restrict light to the three cone classes, we can achieve more contrast, like in that sense. But there are kind of interesting avenues related to color blindness that we're looking into pursuing with the Oz system.
And that brings me to my next question, which is what are some of the applications of this technology and what are you in particular interested in exploring here?
Yeah, so one application that I'm not as involved in is, like I just mentioned, looking into color blindness. So in individuals who are colorblind, they're missing one of the three cone types. And one idea we have is to essentially simulate a third cone type in individuals with color blindness using the Oz system. So you could imagine taking someone who's colorblind, putting them in our system, and just pretending that some subset of their cones are now this third cone type that they're missing, and stimulating their retina as if they had that third type, and seeing, can the brain make use of that signal in order to kind of restore like a third dimension to their color vision. But the avenue that I'm interested in, that I've been working on, is using this system to simulate cone loss. So there are some retinal degenerative diseases that cause cone cell death and loss over time in the retina. And I'm interested in how that affects visual function. So in my newer experiments, I'm just taking any subject and I can, in software, just remove like some percentage of their cones. So show them a stimulus, but I'm excluding a subset of their cones. And how does that affect their ability to, for instance, read text or recognize an image, that sort of thing?
Wonderful. And I also heard that you are a master pattern matcher as well in the jigsaw puzzle world. Can you just tell me a little bit before that, before I let you go?
Sure, yeah. So I am a competitive speed jigsaw puzzler. We just had the national championships in early April, and I'm really excited because I came in second. Um, but yeah, most nights I go home and practice some speed puzzling after my research is done.
Well, wonderful. And Hannah, thank you so much for taking the time to speak with me. I really appreciate it.
Yeah, thanks so much.
University of California, Berkeley researcher Hannah Doyle is one of only a handful of people in the world to have seen the new color Olo. Her team's findings are published in the journal Nature. This is The Best of Our Knowledge. I'm Lucas Willard. There are countless stars in the sky, but determining the age of any individual star is very difficult. A new technique, however, doesn't use light given off by distant stars to determine their age, but instead uses acoustic frequencies. The best of our knowledge is Madeline Reynolds spoke with Claudia Reyes, a postdoctoral fellow at the Research School of Astronomy and Astrophysics at the Australian National University, to learn more.
So a star is basically just a big hot ball of gas, mainly hydrogen, but other interesting things in there too. A star holds itself together by basically because it's so massive, it will tend to collapse under its own gravity, but by burning hydrogen into helium or other elements, it keeps from collapsing under its own gravity, right? So in that process, it emits lights, and that's how we see them and how it keeps us in the Earth warm. Every star is born in a group of stars. So every star originates from these large, huge clouds of gas. So no star is born alone. They're all born in a similar region, so every star has siblings. And that's what we call a cluster. A cluster is just a group of stars that might be bound together. But the thing is, for example, our sun was probably born also in a cluster, but over time, over millions and millions and millions of years, these stars get dissipated into space. But for some reason, some stars, some groups of stars remain bound together by gravity. And in particular, these are very interesting because we know that when a star is in a cluster, has very similar properties to all the other stars in the cluster.
So, what specific cluster did you research into? And just how old is the one that you studied and why you chose this cluster to look at?
So we chose to study the cluster called M67 or Messier Object 67. This cluster is approximately 4 billion years old. And why we wanted to study this cluster? Well, there are a few particularities, but mainly because it has so many stars. So, and the stars are not only in one evolutionary phase, they're in several evolutionary phases. We can study with them from the less evolved, which is less evolved than the sun, to stars that are way more evolved than the sun, and they're huge, bright, huge giants, and even stars that are already stopped burning hydrogen are now burning helium. So there's a huge variety of stars in that cluster that we can study. Another interesting thing about this cluster is that the composition of it is very similar to our own sun. And this is interesting because we know our star the best. So every model that we have generated of stars is basically anchored on what we know about the sun. So this is another reason that made this cluster interesting for us.
So, what are the sound frequencies of stars? And what can you find out about them through the sound frequencies that they have?
Yeah, so some frequencies everywhere, not just in stars, are just waves of pressure, right? So, like in a cartoon, where you would draw a cartoon, you will just draw the little lines, the wave fronts, right? So, in a star, it's something similar. So, something is originating some waves of pressure that resonate throughout the star. And because a star is a sphere, this we can model these waves of pressure like spherical harmonics. And that's how we study the sound frequencies in stars.
So, what do these sound frequencies look and sound like? I mean, how do they present themselves? Are they different depending on the differences of the stars in a cluster? And do they actually make sound?
If they actually make sounds, more of a philosophical question because there's no one there to hear them. But they, it is basically sound because they are called acoustic waves and they are pressure waves. We cannot hear them directly, but we can measure their frequencies. And exactly like you said, they really depend on whatever is, what material is inside the star, what kind of elements. It depends on the size of the stars. It depends on the mass of the stars. It depends on the, of course, density of the stars. Exactly like if you will hit a drum here on Earth, and it will make a different noise depending on the material, depending on the size. That is how the acoustic waves in stars help us understand stars.
So, are the sound frequencies that present in these stars are they different depending maybe on certain characteristics like their size or what type they are?
Yeah, exactly like that, because the frequencies that are excited on the stars, they're excited at all frequencies. But most of these frequencies will then quickly dissipate. But the resonant frequencies really depend on the material and depend on the size of the star. And for example, a really large, huge, evolved giant will have a deeper noise than a less evolved star like the sun.
So, in your research, it stated that to determine an age of a star, it's one of the most difficult things to do in astronomy. So, I'm wondering why is that?
Yeah, so the reason is that age of the star can be really known by what goes on in the core of the star. Because when we know how much of the core they have already burned out, is how we can really tell in what part of the evolution they are. But the way we normally study stars is by studying their outer envelope. So their brightness, because of course that's what our telescopes are designed to look at. So that way makes it really difficult to say, oh, this star has this color and this brightness because of its age or because of what material is in it. So normally it's very hard to tell the age of the star by what is outside of the star. But with this technique, we can tell what's going on inside the star. And that is how we can get more accurate estimations of ages.
How did you conduct the study to look into these stars and to research into their age and their characteristics?
Yeah, so for this study, we really looked into the data that this space telescope is not still in operation. It's called the Kepler telescope, and its mission called the K2 mission. So in this mission, the telescope looked at this cluster for about 3 months, not consecutive, but it looked at the same cluster for a long period of time. And what we can tell from this is that the variations of the brightness is what we look at. What we are interested in is the variations of the brightness. So for me, it's really not very useful to look at a star to get observations. For example, for an hour, like it would be maybe very useful for other techniques. For our technique, we need to look at it for a long time. And why is that? Because if whatever event we register what happens in for a long period of time, then we can convert this event to frequencies. For example, if you make a note every time you get a parcel delivered, you at the end of the week, maybe you can say, oh, I get a parcel delivered twice a week. It's the same in stars. So we get tiny variations at a frequency of maybe, let's say, 100 microhertz, 200 microhertz. We get a peak in the signal. So that is how we study the stars. Then we get a power spectrum and we get the characteristic frequencies of each of the stars. And then we can compare them to models, and that's when the real fun part starts.
What is that really fun part that you're alluding to?
Yeah, so you get the brightness, you get the color, uh, so you have the exterior characterization of the star. And now you can use models that really match that external characterization to generate the possible oscillations that can be happening in the star. And then you compare the oscillations to those models. And now we did a lot of things, and we got actually a couple of papers from this cluster. And one of them was really very precisely characterized the age of this cluster. So our result is 3.95 billion years, the origin of this cluster. And we could see that all of the stars that we study align very well with a particular model of stars of this age. Some other thing that we could see is that we could measure something that is called the small separation, which is just one of the frequency signatures that we can measure from the power spectrum. Our study that was published in Nature really show how these small separations evolved as giants evolved from soft giants to the most evolved red giants. And what we found with this is that the small separations, so let's just call it the frequency signature that we studied, is instead of going from the less evolved, which will have a higher frequency, to the more evolved, we would just have a lower frequency. So it doesn't just happen like that. It really shows you how the the energy generating shell, which is the part that is really doing the nuclear burning, nuclear fusion, is becoming thicker or thinner as the star goes through the evolution part of which starts at the end of the cycle when it's burning hydrogen in the core and when it begins burning hydrogen in a shell. So it really tells you how this shell is becoming thicker and thinner and then evolving into the thinnest part, which is at the end of the giant phase.
So, how does all of this aid our research into our own galaxy, the Milky Way, and maybe even others, like its age, the formation? You talked a lot about evolution, and maybe even the stars too.
Yeah, so this finding really can help us improve the accuracy of our stellar models. And stellar models is a big tool that astronomers use to learn about the universe. So that is one part. Another part is that we know that our galaxy was not born in the same way that we see it now. So it has gone through enormous transformations throughout the years and the ages. So this is very interesting for us to be able to reconstruct how the galaxy became what it is now. And so by being able to characterize the ages of star better using techniques like measuring the frequencies of the oscillations in stars, we can really contribute to have better estimations of stars everywhere in the galaxy. And by knowing how old they are, knowing when each one of them originated, we can have a more realistic picture of how this evolution came about. And maybe even model how the galaxy will look like in a few of billions of years.
Well, that's really cool to know that we can map out possibly what our galaxy will look like into the future. So that's really cool. So, what are you looking forward to in terms of research, maybe into this topic specifically?
Yeah, so more immediately, what I would really like to look is to look at other clusters, maybe other stars in the field, not necessarily in clusters. And I would like to try to see if this feature in the small separations is really telling me the same that it's telling me in this cluster. So I want to be able to use this cluster as a benchmark and see if I can see the same in other stars.
Claudia Reyes is a postdoctoral fellow at the Research School of Astronomy and Astrophysics at the Australian National University. Her research into the acoustic frequencies of stars is published in the journal Nature. She spoke with the Best of Our Knowledge's Madeline Reynolds. If you'd like to tell the Best of Our Knowledge what you think, send us an email at knowledge@wamc.org. You can listen to the Best of Our Knowledge anytime as a podcast, downloadable wherever you get your podcasts. If you want to catch up on past episodes or hear more WAMC National Productions programs on the news, academic study, books, women's issues, the media, and the environment, visit wamcpodcasts.org. This has been the Best of Our Knowledge, episode 1806. The Best of Our Knowledge is a national production of WAMC Northeast Public Radio. Thanks to associate producer Madeline Reynolds. The latest on all National Productions programs is available via the Airwaves newsletter and our flagship station's website, WAMC.org. Until next time, I'm Lucas Willard.